Now that we've looked at transactions, we can move on and understand ACID, A-C-I-D. ACID stands for atomic, consistent, isolated, and durable. You'll see this term a lot related to databases. SQL databases make a big deal about the fact that they're ACID, and more recent thinking, though, has suggested that maybe ACID isn't such a great goal, or at least not the way it was originally conceived. But before we can even dig into that, we need to understand what's going on here. I'm going to take these out of the order of the acronym because I'm going to do the easy ones first. Atomic, all or nothing updates. Yeah, that's what we've been talking about with transactions. Transactions that you could commit or roll back. We change multiple tables. We've seen examples of this, or multiple bank accounts. Either all the changes happen or none of them happen. This should be pretty straightforward. Also durable. Durable basically says I can walk up to the computer where my database is running and pull the plug, and when I plug it back in, all the committed data is still there. Until recently, this meant that we had to wait on a write to get pushed through RAM and actually change a magnetic disk or tape. The computer, and maybe I haven't emphasized this enough this semester, but typically a CPU is 100,000 times faster than a disk drive. And so if we can get away with caching stuff in memory, which we can on a read, if I read something and I read it again, I can just pull it out of memory instead of going all the way down to the slow disk. But when I write something, it's not good enough to just change that in memory, because if I pull the plug and plug it back in, the memory is gone. To make sure it stays, for it to be there when I get back and plug it back in, it's got to go all the way out to the disk and change the disk. And for that to happen, it takes a lot longer than it does changing the memory. Things are starting to change. Now we have SSD, solid state devices. Basically, this is memory that doesn't lose its positions when it loses power. And we're seeing these a lot. For instance, if you've seen a little card to go into your camera or your cell phone, those are SSD materials. But SSDs big enough to hold a whole database are still rare, although they're on the horizons. And even then, SSDs are noticeably slower than RAM, random access memory. So in general, durable means that we don't consider a commit to be complete until we know that it's all the way through the system has actually changed the magnetic material on the disk drive. So we're willing to have the trade-off of things taking longer in order to ensure that the data is really saved. So that's durable, and it's pretty straightforward too. Now, our others, consistent and isolated, they're a little harder to understand, and they really deal with multiple users interacting with each other, or even one user interacting with himself. But here are a couple of the kinds of problems that bring up this issue of consistent and isolated. Let's assume that a user runs a large update. Maybe they run an update with a where clause where they change 500 records in a 500,000 record database. This is going to take a while. And what does another user observe while this is going on? Suppose I get some of my records changed, but not all of them, and another user starts looking at records. What do they see? Yeah, it's an interesting question. It becomes almost philosophical. Or take a transaction that affects multiple tables. We've seen some of those. For instance, Kroenke's example of updating the customer record, updating the salesperson record, and then writing a new sale into a sales table. What do other users observe? Does anyone ever actually pick it up when the customer's record has changed, but the salesman record hasn't changed? What if I'm doing some set of queries related to that? So really the question for both consistent and isolated is, what do other users observe in the database while we're in the middle of changing it? There's a time element here, and there's a perspective element here, and they make it kind of tricky. Let's try to dig a little further down. So consistency has been defined as any transaction started in the future sees the effects of other transactions committed in the past. Okay, when do other users see the change? And consistency basically says once my commit fires, then anyone that starts a new transaction after that commit should see the commit. This seems obvious, but it can be hard to do when we're trying to maximize caching and usage of memory, things like that, particularly as we network different machines together with databases. It gets harder and harder. We'll talk more about this. Isolation. If a transaction affects multiple tables, can other users see parts of the transaction, which could even get rolled back? For instance, I'm creating a purchase order with the purchase order record and a bunch of purchase order detail records. I get the purchase order record itself created, but the detail records haven't been committed yet. Could someone else see a purchase order with just that header and with no detail items? Hard to know. SQL tries to give the programmer some control over this, and this is not something we're going to get further into in the course, but I'll just mention it to give you some idea of what's going on. And this is one of these classic examples that the more control you try to have, the more you have to keep track of. So SQL identifies 3 isolation-related problems. Dirty reads, that is, I read something after you've changed it, but before you've committed it. Should I see that? Maybe I should only see the database the way it was before you started your transaction. Non-repeatable reads, changes made by other users while we're in a transaction. I start my transaction, I've done some reads, and while I'm trying to make changes, other people have made other changes. Do those ever create a problem for me? And finally, phantom reads. So we do a read and we see maybe we get so many records, and then later in our transaction, we do another read and we find records that our first read didn't find because between those 2 reads, things have happened, okay? SQL allows us to set isolation levels that can avoid each of these problems, but the cost of using more resources. Often it's having more locks, okay? So for instance, the phantom read, I can avoid that problem if I lock the whole table instead of just locking parts of the table, but that means other users have to wait. Or in some cases, to solve these problems, we take sort of a snapshot. When we start a transaction, we figure out all of our reads at the beginning, or maybe we save and cache all of the data the way it was in the database at the beginning of our transaction. That takes care of our problem, but it takes a lot of resources. It takes a lot of memory. It requires a lot of effort on the part of the hardware. So we can set isolation levels to avoid these problems, but at the cost of using more resources, typically locks that slow other people down or trying to hold on to more memory and caching. For instance, we could do a read at the beginning and then save all of that someplace private to us and do all of our work on that until we do the commit. But once again, that takes more space. Why is ACID important? Traditionally, we want all the users of a system to see exactly the same data, and we can consider some real-world examples of this. Consider a husband and wife sharing a bank account. Shouldn't they both see the same balance when they consider withdrawing money? They each walk up to an ATM machine on different sides of town, and they look at their balance to decide how much cash they should take out for some purpose. What if one's just taken some cash out, but the other one, when they look, they don't see it? Maybe they both do an inquiry, and then they take a minute to think about how it's going to play out. And during that minute, the other person takes some money out, right? And they go, gee, I know there's $100 there in the bank account that's unused. I can go ahead and withdraw $100. But in fact, by the time they get around to actually withdrawing the $100, not all of the $100 is still there. Or consider picking out airplane seats next to each other for a family. A lot of families want to sit next to each other. I'm sure you can see how that would work. Let's suppose we have many, many customers that want to buy a ticket on that flight, and they're all trying to pick their seats at the same time. While I'm picking my seats for my family, suppose I get around to picking one, but there's a little pause before I slide next to it and pick another seat. What happens during that time? Is that seat available? Well, it has to be, because the computer doesn't know I'm about to pick the seat next to mine. It doesn't know that I'm trying to buy for a whole family. It's just saying, hey, pick some seats and we'll tell you how much they cost, particularly if you have a bunch of kids. To pick out, say, 5 seats, it might take you a few minutes. Husband, wife, 3 kids. By the time you click all of those, time has gone by and other people have tried to grab seats. What if they grab one of the seats I'm trying to grab for my family? Is there a good way to start over? Or when I try to commit that, does it simply say, oh yeah, some of the seats you pick, other people have been quicker. By the time you finish picking your 5 seats, some of those got picked by other people. ACID ensures that things work in this way where we all see the same data. And it was long considered the gold standard for database. But we're going to see as things get networked and as things get busier, ACID starts to become a problem that gets in the way as well as a tool that becomes helpful. And we have to look at a lot of trade-offs. But before we can, we have to understand what ACID is. And then next, we'll start looking at why ACID is becoming a problem in the networked age.